Hello. Good afternoon, one and all present here. We, on the behalf of CROW, an initiative by the Department of Mathematics, Presidency University, Kolkata, want to welcome you all with warm regards and gratitude for taking your time to register and be present here. So, what is data without privacy? It is like a diary with unlocked pages, a whisper shouted into the crowds, a treasure chest left open on the street. Cryptography plays an important role in ensuring that our data remains private and secure. But as we move towards the future, towards quantum computers, which are predicted to be far more powerful than even today's most advanced supercomputers, an important question arises. Will our current methods of protecting privacy still keep our data safe? So here we are, gathered to answer and question our questions on the topic, the state of the art issues in quantum and post-quantum cryptography. Now, I would like to call on stage the head of the Department of Mathematics and the founder president of CROW, Professor Abhishek Odikari. Sir.
So good afternoon all. So in spite of this bad weather and traffic, so you're all here. Thanks for that. On behalf of CROW, so this is an initiative by the Department of Mathematics, Presidency University. It's our great pleasure to welcome you all to this auspicious occasion. So this department is one of the oldest departments in India. Started in 1817, having heritage of more than 200 years. So we are proud of our eminent alumnus like Meghnad Shaha, Radhanath Shikdar, Nikhil Sarkar, Satyendranath Bose, Sher Ashutosh Mukhopadhyay, Azizul Haq, and of course, Manik Bandyopadhyay. So many of you may not be aware of the fact that the Bengali সাহিত্যিক বাংলায় সাহিত্যিক মানিক বন্দ্যোপাধ্যায় তিনি আমাদের প্রাক্তনী ছিলেন। The four vertex theorem, Shyamadas Bandyopadhyay was one of the alumni of our department as well. So our department wants to continue its tradition of great academic work. To help us fruitful this goal, we have established in 2025 the Computational Research and Operation Wing, in short we call it CROW. This is an academic student-driven, mind that this is a student-driven wing, which was founded at our department. So the basic idea for this was to do some interactive, collaborative and multidisciplinary work among different departments on computation. So it has been found by us that in many departments we have seen that many students are really good in programming. So it would be a kind of common platform where you can work together to have some results, or you can participate to some hackathons as well. So last year in 2025, I'm glad to inform you that from our department as well as from Presidency University, we participated in 2 hackathons as well. So another initiative was taken by us. It was 12-day boot up. What is that name? So basically to introduce a basic level of Python programming, and the name was I think, what is that name? Yeah, so that was the departmental initiative where we had a 12-day program for the beginners of Python programming, and we successfully completed that, and the certificate were also distributed among the successful students. So another initiative was or is for this CROW is to organize regularly in a certain interval the invited lectures by eminent personalities like Subhamoy Maitra, who is present among us. So in spite of his busy schedule, he has given us time and we are thankful for that. So today you are going to witness his knowledge on quantum crypto. Though you might be mostly, you know him as an expert in Star Anandu, but it's a different way that he is going to talk today. So that's all about this, and we are really thankful to Subhamoy Maitra as well as all the participants. The important part was that I was just looking at the registration, and there I have seen that more than 40 institutes, the students from more than 40 institutes, they registered for that, for this event. And I hope that many students will also join us. Maybe they are on the way. Today we had some traffic due to Prime Minister is visiting Kolkata, and also it's raining. So we hope that some more students will join us. And before I leave, may I request the students to formally introduce Professor Subhamoy Maitra of Indian Statistical Institute. That's all. Thank you very much.
It is my honor to introduce our distinguished speaker, Professor Subhamoy Maitra. He is a professor at the Indian Statistical Institute, Kolkata, in the Applied Statistics Unit, and a renowned expert in the field of cryptography and quantum information. Professor Maitra completed his bachelor's in engineering in electronics and telecommunication engineering from Jadavpur University, and later earned his PhD from ISI Kolkata, with his research focusing on cryptographically significant Boolean functions. Over the years, he has made outstanding contributions to the domains of strings and block ciphers, Boolean functions, cryptanalysis, and quantum algorithms. He has published nearly 200 research papers in leading international journals and conferences, and his work has received wide recognition with thousands of citations worldwide. We are indeed privileged to have him here today to share his insights on the state of art issues in quantum and post-quantum cryptography. Now, I would like to call on stage Professor Subhamoy Maitra.
While we prepare the presentation, all of you understand Bengali? Is there anybody who, no, easier question is there anybody who cannot understand Bengali? That's good. তাহলে আমাদের দুপুরে এমনিতেই ইংরেজি শুনলে খুব বেশি পাবে আর কি, সবাই ঘুরে ঘুরে থাকে, আমরা চেষ্টা করি মোটামুটি বাংলা ইংরেজি মিশিয়ে একটা বলার এটা very interesting thing is let's talk a little bit about politics of academics, like thousands of citations. I have something like 8,000 citations, and if you write 200 papers, not all the papers are outstanding, naturally. How can one person write 200 papers, each of them are outstanding? And the names and images that Abhishek had already shown, after that it's better not to talk. But I had earlier also another opportunity talking in this seminar room. Thank you very much for inviting me. The most important part is while I'm presenting a lecture in a mathematics department, the main confusion in between mathematics and computation is the way mathematics was moving in our country as we learned differentiation, integration, what is limit and all those things, which is my understanding, it is something like in the domain of real. And when we come to computers, it comes in the domain of more or less discrete kind of mathematics. Now, generally, earlier trend was that serious mathematicians, they do not consider this discrete mathematics as a very serious topic. So, a very good mathematician like Borel, when he meets Professor Vimal Roy, who is actually our leader in the domain of cryptography, say in Cambodia, then he tells, oh, one more failed mathematician who is doing cryptography. So that is one aspect of the history of mathematics. On the other hand, we all know that we are market driven, right? So, and there you need to write programs. Whatever is happening around us is that some some people are giving instructions to this computer. This is a very good computer, by the way. So might be as good as this one. And on those programs, we are interacting with those programs. And one more thing we have to understand very clearly, that is, there is not much difference between hardware and software. What is hardware? That generally say I am doing multiplication. For multiplication, there can be one circuit. You can do school book multiplication. You can take n bits. You are multiplying it with another n bits. So bit multiplication circuit you can do by AND gate. 1 into 1 is 1, and 1 into 0, 0 into 0, and 0 into 1 is 0. So AND gate will give you that output. So using AND gate and some other gates, you can design a multiplicator circuit. Now, for each algorithm that you are writing, if you have to generate one circuit, then it becomes very hard, because every time you have to arrange a fabrication lab and all those things. So what we do, we create a computer which contains huge amount of circuit, and we mostly do not use more than even 1% of that when we are writing programs. So this computer is a general purpose hardware. The way it is designed is, whoever likes to generate a circuit, better allow that person to write something that will be transformed into some low level or machine level instruction which will be executed in a circuit. So this is what a computer is. When we look from our side as engineer side towards mathematician side, the gap that we find is something like that. Say when we talk about manifolds and all those things, very complicated mathematics, then we clearly understand that we do not know those things. So whatever mathematics we do are mostly 10+2 mathematics and something like maybe undergraduate level mathematics that we implement on a computer. Even if you like to implement a finite field operation in a computer, that is very complicated to write down those programs. On the other hand, there is a problem in the people who are working in mathematics in some part of our country, around the world also, that they think that this computation as a subject or programming and all those things are generally not very intellectually motivating exercises. So that part we do not agree. What we tell is writing a program, talking to a machine is also very complicated. It requires high intellectual capability, and additionally we have a market side. So the initiative that Abhishek is leading here, which is CRO, which talks about computational, and there we need to write down programs. So now a mathematician who is really very good, exceptional, he may write a few things by hand and prove something and may earn his or her bread with that. But generally the market tells that if you have a logical mind, and mathematicians have the most logical mind, because for them A and not A will have different values. In politics that never happens, in social sciences that never happens. In physics also there is incompleteness and uncertainty. In mathematics also there is uncertainty. What is there is incompleteness. What is the incompleteness? That I know that any even number can be written as the sum of two prime numbers, but we cannot prove that. So we know that this is incomplete. But otherwise, the probability and all those things, while we model uncertainty, they are also, every step that we talk about are absolutely logical, and I should not use the word deterministic, but when I am telling this happens with probability this, I am estimating this, all my statements are very concrete. So this actually connects us that the domain of discrete mathematics and the domain of computation is very well connected. And when we have a computer, so if you think about George Boole, I think 70 or 1800 something, just after around that time, 1760 to 1840 is possibly understood as Industrial Revolution. So that time, actually, the technological development was huge at that that time, and George Boole was the person of that time who was actually a philosopher and also a mathematician. He told that everything can be done with zeros and ones. Everything, almost everything can be done with zeros and ones. So that idea immediately we could not follow, but in 1900 something, Alan Turing and von Neumann, they have provided the model of computation, the model of classical computation. Why it is called classical? Because that model of computation is related to Newtonian mechanics, some kind of, what I would say, standard ideas of electromagnetism, current, voltage, and all those things. And they understood that if I put a battery, say 1.5 volt, if the top side I consider as 1 and the bottom side if I connect, we consider as 0, then that way, using current and voltages, I can design circuits. So these circuits are mostly based on ones and zeros, but at the same time there are circuits which can correspond to real mathematics also. What is that? There are ideas of operational amplifiers. If you use operational amplifiers, means that you can design differentiator, integrator, and all those things. But that didn't become popular because this discrete domain, working with ones and zeros, that had a huge advantage, that the amount of error, if you can distinguish a 0 and a 1, that distinguishing capability in a circuit developed at a very high speed. Instead of distinguishing 1.5793 and 2.1329. So they understood that so what they understood that if we can actually identify zeros and ones properly, then that would actually be the perfect thing. Actually, this is my new phone, and I do not know how to put the sound up. So this is the scenario. So ones and zeros are properly understood. Ones and zeros are properly understood means 5 volt is 1, say in these computers. So our alternating current is coming, and then there is some kind of SMPS which transforms it to DC, and then we keep the voltage a little bit down and then make it 5 volt and 0 volt, and with that we have huge amount of circuits where I can put zeros and ones and compute those. So basic idea of von Neumann and basic idea of Turing. Turing's idea was something like, if you remember cassettes, you might not have seen those, then there is a head of the cassette and the tape is moving, and von Neumann's architecture was something like, you have one processor and you have one memory. So data is in the memory, something like on the exercise book, and from the exercise book you are reading 3, you are reading 5, adding in your mind in the CPU 3 plus 5, and you are getting 8, you are putting that in this. So this development came up, and this development 1914 to 18 and 1939 to 45, we had 2 world wars. So you must be knowing that any kind of war, they always have been getting better technology. Cryptography was developed at that time. Imitation Game is a very special movie by Alan Turing that you should watch, and that way it developed. Around 1970, we had good computers by IBM, which were actually commercial computers that came to our country. Before that also in 50s and 60s, there was good amount of research in Indian Statistical Institute and Jaipur University, though that computer I wouldn't say it's a good commercial one. So there was very serious work, and then what happened in our country? Our country came in fabricating the chips and all those things, the circuits, very late. During 80s, when we were students, we had a semiconductor complex limited in India, Chandigarh, and that was burned either by accident or by some political initiative. And after that, we have done very little in hardware. So our strength is not building hardware. So this computer, if you try to find out, there is a very little chance that even it is assembled in our country. So the maximum that we do is we do assembly. Now, this is the scenario of classical computer where we have the best computers of the world in our hand, and the development took something like in 1900 something to 2025. So 100 years, we are more or less ready with all the developments. The computation and communication is revolutionary. Now, is there any other computing model? So there are many computing models, like non-determinism is another computing model which cannot be implemented. That is why it is called non-deterministic finite automata or those kinds of things, on which what you get huge power, but you cannot implement it. Now people thought about parallel computation, that is, if I have one CPU, I can do this thing. If I can have the CPUs as an array, so say 1024 into 1024 CPUs, if I can do that, will surely run much faster than one computer. And in fact, inside this computer also, we will possibly find 16 cores or something like that, or 16 processors are there. Generally, when we write programs, we do not use those processors. But some people can really write programs and check that whether all the processors are being used. Now, during the First and Second World War, already quantum physics related things were becoming popular. But people have not thought seriously about a quantum computer because the physics and the mathematics was little different. So what then? They planned that the classical computers were developing. There was not much effort related to development of quantum computers. But in 1960s and that time, in fact, there was a paper called Quantum Money. I will try to talk about that also, that bit can be copied, but a qubit cannot be copied if it is unknown. So from that, the concept of quantum money came. So Weisner has written a paper in 1970, and naturally that paper was not accepted. People are not getting the idea. Later in 1982, when DA and many other people have shown that this no-cloning, famous no-cloning theorem, then people understood that okay, there are very important things involved in these papers. So I would say that Weisner's paper is one of the seminal papers. So the mathematics is simple, the idea is simple, but he understood what is coming in the future. The paper was accepted much later in 1983, 13 years for such a simple paper to be accepted. And it is not very old, 1970, that time people were very good in physics and mathematics. So these are the questions that I never get the answer. That in 1970 he wrote a very clean paper which is clearly understood mathematically, and people could not publish it till 83. Similar to that is BD84 algorithm, which was, the paper was more or less Bennett and Russell, which is related to quantum field distribution. They understood in 79. They told that in many places people were not convinced. Finally, in a very, what I would say, moderate conference at Bangalore, they were invited and they presented the paper in 1984, and it is famous as BD84. So these are very interesting stories, that at that time the science was not that poor that people didn't understand the value of these papers, but they understood in one example after 13 years, in another example after 5 years. There is a brief history of this BD84 paper you can find. There are lots of stories there. So these, at that point in 1980, Feynman, he was then very old, other than physics, he was also thinking about world politics, he was involved in the Challenger accident investigation, very interesting stories. He has given a lecture where he told that, okay, there can be a simulator which is based on the ideas of quantum physics. So he has given the lecture possibly in 1980s, and in 1981 it was published in IJTP, International, possibly IJTP, International Journal of Theoretical Physics. That journal is not very competitive nowadays. You can easily publish papers in that journal. But the Feynman's paper was also published in that journal, and immediately people took it very seriously. This is another very interesting thing. That people are talking about that, nobody is getting convinced, and suddenly a person who talks well, Feynman used to talk very well, so, and he was popular in the market, so when he talked, then people became serious. Then we had several algorithms that has shown that quantum computers are much more powerful than the classical computers, and in 1994 it has showed proof that if you give the product of two large primes and if you give them product value, then from that we can easily find out those primes. That is famously known as Shor's algorithm. And from that time, what happened? People understood that okay, all our crypto systems are actually based on this, all the public crypto systems, all our banking transactions and everything. Now that would have a tremendous effect, or other way you can say a devastating effect on classical public key cryptographic systems. Now consider the year. The year is 1992. Second half of 1970, classical public key crypto systems came, and they at that point of time, around 1992, internet has not come very seriously. So communication, secret communication was not that popular. But at that point of time, all the people knew that the classical algorithms that we are implementing are going to be broken if there is a quantum computation. Everybody knew that at that time. The model of quantum computation was very clear. But still, we started developing RSA, previous Shagi and Erleman algorithm, and elliptic curve crypto systems continuously till 2015-16, knowing very well that quantum computers are coming or there is an attack model. In cryptography point, those who are people in Abhishek group must be knowing that if we get a crypto system which claims that I generate zeros and ones uniformly at random, so then the consecutive zeros and ones should not depend on an independent. It should not depend. So it's a material IID kind of thing. So it should not depend on the previous bits, or there should not be any bias. So if I find that the probability of this bit XOR this bit XOR this bit XOR is addition over GF2, then the probability of that bit should be 0 or 1 should be half. Now if somehow somebody shows me that the probability of that is not half, but it is half plus 1 by 2 to the power 5, then immediately I tell I won't use this crypto system. That is the standard practice. Now this is another important question, that on a computational model, clearly people understood by 1995, maybe say it took 1 year to understand Shor's paper and to check it is correct. It is not a very hard paper, understandable. And then people understood by 1995 that classical public key crypto systems are will be completely attacked by quantum computational models. But still there was no serious effort in post-quantum cryptography. That means that I know that quantum computers will come, and knowing that also, I was using the algorithms which were more or less popular at that time and made all the standardizations with that. This is very interesting, and another political aspect of cryptography that I am trying to find the answer. It's very hard because it's not mathematics. Somebody thought in some manner. Then in 2015, some pages not coming there. Oh, this is the slide. So in 2015, NSA is the top cryptographic body of USA, National Security Agency. They told that no, now if you like to put more money on elliptic curve and RSA kind of thing, you should be careful and you should actually consider post-quantum cryptographic algorithms towards this purpose. And from 2015, there was huge effort in the direction of new crypto system development. Earlier it was known that discrete log based or factorization based cryptographic algorithms, the public key cryptographic algorithms are not good. But the serious effort people put during this time. So what happened then? people are coming together to design algorithms which are not based on these number theoretic things. These are mostly number theoretic things. So what are the other things? Other things are more or less based on lattice kinds of things which are, I should not say those are vector spaces, but with integer coefficients. I'm not getting into mathematical details. So on some structures, and another is based on coding theory. Coding theory is you encode something, decode something using those kinds of things. There were certain algorithms. Those algorithms came, and then in last few years there were huge effort. And what we got finally, we got a few algorithms which are standardized around the world. So what are these algorithms? I'm not again getting into what is public key encryption, key establishment, what is digital signature, but you can just remember these names, that there are 4 algorithms: crystal Skybar, crystal dilithium, Falcon and Sphinx. These are the algorithms which will actually protect you against a quantum computer, which is very powerful, and these algorithms do not require any quantum resource. On this computer, on this mobile phone, you can run this algorithm. And in the latest development, on March also, they have added one more algorithm, which is known as HQC. So total 5 algorithms now. So what is the message? The message is we already have RSA kind of algorithm, we already have ECC kind of algorithms, but those algorithms we understood by 1995 surely that those algorithms cannot be used for a long time if a quantum computer comes in the market. And we took almost 20 years from 1995 to 2015 when somebody from USA told that no, you have to write down algorithms using other primitives. Then the world started working like this. So when we talk about that we are not having developments in India, it is not only India, it is around the world. And this discussion that I am doing now, that does not need any hardware fabrication also. A mathematician can do it on his own. So 20 years we invent what? And one idea could be that the discrete log problem or the factorization related problems are very easy to understand. More or less a BSc first year, second year student of mathematics can understand how a public key is created, a private key is created. When we get into these algorithms which are supposed to be resistant against quantum computer, we have to use many other mathematical arguments which are based on lattices and all those things. So this is one problem. Understanding these algorithms, again believe me, I also do not know each and every step of these algorithms. If you ask me the steps of RSA, I can immediately tell you, choose 2 large primes, multiply them and calculate. So A equal to PQ, then you calculate phi n, which is P minus 1 into Q minus. I remember every step and I know what are the problems, because I should say that we are fed with RSA algorithm. We are fed with elliptic crypto system. We have to learn those. So we remember, we are discussing always. But now when these algorithms came, these algorithms are not very easy to keep in your mind. You cannot remember. Some people must be remembering. So now learning these algorithms are becoming very important. So the students of mathematics and programming who know good mathematics and who know good programming around the world, there is a huge requirement of people understanding these 5 algorithms. Understanding each algorithm for a good student should take something like 3 to 6 months. So it requires a good time, but at the same time it is always a very good investment to understand these algorithms, because even if quantum computer does not come, there will always be a threat that sometime surely quantum computer will come. We call it Y2Q, year 2 quantum. Something like you might be knowing the Y2K problem, that all the softwares had to be changed because earlier year was of 2 digits and suddenly people realize that 2000 will be 00 and 99 will be 99. So 99 and then it is 00, subtraction and all those things won't work. There will be a chaos. So they have to change the software. Similarly, they are using the term Y2Q. So So they are expecting that a good quantum computer will come. I'll possibly try to come back to the stories of quantum computer a little later. So one very specific message is there are algorithms which are classical. They will work on these computers and they are resistant against a quantum computer. So this is the idea, and given that the other parties, when RSA and all those electric curve based algorithms were happening, at that point we know how to optimize them. How can we run those programs very fast? And when we started working on these algorithms, we initially found that these algorithms are taking quite a lot of time. Like you are using WhatsApp. In WhatsApp, what is the public key part that is being used? Elliptical cryptography. So it is running very fast. Now, only very recently there are in some browsers, this Kaiba has been implemented. So now, what we understand that even if in these good computers, the computation might be much higher than what we did for RSA and elliptical cryptography. And also the packet size, because the key size, earlier say the keys were 512 bits, or the keys were for elliptical it is little less, say 256 bits. Now the key sizes are more or less 8,000, 9,000 bits. So you need to give more space. What does that mean? In all the computers, around in 2 billion equipment around the world, we have this public key infrastructure implemented. And it is not that you bring out one code and put one code. It is very hard. This migration, any software update kind of thing, that takes a huge effort, huge money to implement the infrastructure. So many countries are doing that, which is known as the National Quantum Mission. In our country also, prime government is trying to put a lot of money. So even if a good quantum computer suddenly comes in the market, or somebody gets convinced that US or China, they have built a very good quantum computer, then these migrations will be immediate and there will be huge money coming into this domain. Otherwise also there is, I would say the difference is between billions and trillions. Now billions of dollars are invested. On the other hand, trillions of dollars will be invested when people will really understand the threat. But now we are ready with our solutions on classical computers. So whatever we told, thinking about quantum computers, what are the protective mechanisms? Now, the basic idea came with quantum computers. So quantum computers, the notations are not coming properly, but the basic idea is, earlier we have zeros and ones in quantum computer. We have a qubit as something like alpha 0 plus beta 1, where these zeros and ones are, this column vector sign is not coming. So 0 is represented by a column vector 1 0, and 1 can be represented by a column vector 0 1. So if I consider a qubit alpha 0 plus beta 1, then it is alpha into 1 0 and beta into 0 1, which is alpha beta. Okay, so by this we represent one qubit where alpha and beta are complex numbers such that mod alpha square plus mod beta square equal to 1. That is the basic mathematical definition, and it is actually implemented using different kind of devices. Technologies are developing. As you understand, when we started working on classical computers earlier days, there were lots of errors. Similarly, same things are happening. What technology we will take, there is huge amount of error. For storing a qubit, we need minus this amount of temperature. We need some diamond related elements which are very costly. So these problems we are moving around, like similar to, I would say, that around 1340, 50, 1930, 1940, 1950, 1960, that kind of time we are moving through. Where we might have a computer, but it is almost non-accessible to common people. We cannot have any access. In India, I do not know, and there are some places where we can have certain stories that quantum computers are actually being built. So, since we have only 20 more minutes, so I will not get into much mathematics. So, one question is very important, that in one bit, 0 or 1, we have some information stored. Okay. Similarly, when I take one qubit, it is alpha 0 plus beta 1. What is alpha, what is beta? Both are complex numbers. So I can have actually infinite amount of, in fact uncountable, we can say, that amount of information I can store in a qubit. Yes, theoretically we can do. But if I have a qubit where I store all the information, I give it to somebody, that person has to understand what is there inside. That part is very complicated and very informally telling that with a qubit you can store something like two classical bits, not more than that, so that you can understand easily what is there inside. So don't think the basic question that will come that if I have a qubit, I can have infinite amount of information there. That is not correct. This is one thing. There are multi-qubit states, but slides are not coming properly. Then we come to certain kinds of idea. I should be able to let me go. This superposition. In classical bit we have zeros and ones. In quantum bit we have alpha 0 plus beta 1. This is called superposition. This gives us a huge advantage related to quantum parallelism. What is the advantage? The advantage is within, consider you have n bits. So how many patterns are there corresponding to n bits? 2 to the power n. So if you have 8 bits and if you want to write down all the 8-bit patterns, it is 2 to the power 8 equal to 256. So you have to write down 256 patterns. If it is a 100-bit pattern, then it is 2 to the power 100, and you will never be able to write down 2 to the power 100 many patterns. This is the problem with classical computer. On the other hand, if you take a quantum computer and if you take 100 quantum bits and if you just put 100 Hadamard gates, then in the output you will get all the 2 to the power 100 states with equal superposition. That means with linear amount of resource, you can actually generate something which has exponential amount of outcome. This gives you the idea of parallelism. So the idea of parallelism comes from quantum superposition. The next important thing is entanglement. Entanglement, I try to give this example. This page is more or less coming well. So consider I have two qubits. If I multiply them, since it is in matrix notation, this multiplication is basically tensor product. It is, but you can understand it in an algebraic manner. Now consider this gamma 1 0 0 plus gamma 2 1 1. If you do that, you cannot write it as a product of these two things. And this is called entanglement. That is, if there are two particles and say you have created such an entangled state and you keep one particle with you and through a quantum channel you send another particle to some other person and then cut this quantum channel. So even if the channel is cut, these two things, these two particles will be connected to each other through entanglement. So this is another aspect which was not there in classical communication. That is, the things, the bits are not connected to each other. In the memory, when you keep bits or when you are communicating, each bit is actually an independent entity. They might be packed somewhere. But here, you can have two qubits which are such that they are connected without even any channel if they are communicated earlier. So that means when I am working with a machine and then I give you the machine, by that time I can always have entanglement with another machine, and when you buy that machine from me, you do not know that you are always sending information to us without any channel. So this is another resource. This has some advantage in cryptography. These are some kind of problem in cryptography also. And this gives actually the idea of device-independent quantum cryptography. So you can just remember the terms. And the last thing is, which is important, is the no cloning theorem. What it tells that if you know some qubit, you can always generate the similar qubit, many of them. But if I get a qubit from somebody, and I want to process that, I really do not know what is there inside. This is the problem. That means in classical domain, whenever you are communicating something, at that point the problem is at that point you can always get the data. So I am communicating, I am giving you my mobile, then you can actually copy all the data without getting any interpretation of it. So you do not understand what is the data. It might be encrypted, but you can copy the data. In quantum domain, if I give you a qubit, you have to just sit with that. You cannot copy that to another qubit without knowing any information about that. What does that mean? When I am communicating through an open channel, some qubit, if somebody else tries to copy that, my qubit will be disturbed or destroyed and I will immediately understand. So here the mathematics is very simple. So again I possibly told that about this paper, Weisner's paper, 1970, money cannot be copied. From that idea he told. Later there were papers by Zurek and DX in 1982. Then people understood the importance, and this is the statement. It is not possible to copy an unknown quantum state. Consider a quantum slot machine with two slots labeled A and B. A is the data slot set in a pure unknown quantum state psi, and B is the target slot pure state S, where A will be copied. So this is the idea, that is U psi S should be psi psi and U psi S should be phi S should be phi. Now U is a unitary operator, which is the quantum gate. Quantum gates are always understood by a unitary operator. You can take unitary matrices. So if you do little bit of mathematics, you will find the inner product of psi and phi equal to inner product of psi and phi, that is square. So if x equal to x square, then what are the solutions? X equal to 0 and x equal to 1. So the inner product of two things would be either 0 or 1. What does that mean? Either the two things would be same or the two things would be orthogonal. Only in that scenario you will be able to copy. Otherwise, you will never be able to copy anything that you are communicating. So, based on these, you can also tell that you cannot distinguish between two quantum gates. When you read 0 and 1, you understand this is 0, this is 1 with certainty in a classical computer. In quantum computer, you cannot do that. Now, quickly through little more stories. What is the actual hardware software issues? Up to 4 is fine, take 10 more minutes. Yeah. So this is a very important document. This person is very famous also. You can read his many documents are understandable, and he is one of the most competent person in this domain. What he told that in 2018, he told that noisy intermediate scale quantum computers, which is known as NISQ, that will be available in your near future. Yes, we have. Quantum computers with 50 to 100 qubits may be able to perform tasks which surpass the capabilities of today's classical digital computers. But noise in quantum gates will limit the size of quantum circuits that can be executed reliably. It is very simple. When you are listening something, if there is a lot of sound, then obtaining what you want to listen, for that you have to put more effort. So if there is more problem, if say you are multiplying, when you are or adding, if you know that every step there is some possibility of error, then you have to take care of certain other parts of the algorithm. It will be more costly. Similarly, this is the problem with the quantum computers now. So, if you get a 50 to 100 qubit quantum computer that Google or IBM, they are telling, yes, we have implemented those, that means yes, it is very good. But will that help us? The answer is still not very clear. So the quantum computers that we have and the power related to them, what they are claiming, are really, what I would tell, that really not very, something that immediately we have to consider about, that the quantum computers are already coming and we should be very careful. That part is also not clear. So now you are understanding the market scenario. Corresponding to a market, we have some term which is known as TAM, totally accessible market, and all those. Huge money is the amount of money that will be invested in this capitalist system on this market are decided by those. So, TAM is total addressable market. But people are not sure when they should go for the migration. And on the other hand, when they will get actually a quantum computer. So, who are working? IBM is working, Microsoft is working, Google is working, Rigetti is working, DOF is working, and they are claiming a lot of things. Very recent news that you know, that this is a famous statement by Pichai, which is telling that very complicated challenges can be solved by these quantum computers. But the problem is, what is the most important thing when you get a quantum computer? You want to factorize. So, can this computer answer that whether we can factorize it properly? No. They are taking different kinds of problems which is related to a random circuit, because in quantum domain they cannot really implement the circuit they want, and based on that given random circuit they are finding out some synthetic problems where they can show that these problems cannot be solved on a classical computer quickly, but this can be solved in a quantum computer. That is the only thing they are telling on very specific synthetic kinds of problems. So there is a huge gap between what they are claiming and what will actually affect us. So in this regard, I will try to say one story which I have followed very carefully. So this is a story that I have followed very carefully. This is the report. So Xinhua 26, of course Xinhua is something like a newspaper, not a research. So it would always have propaganda. So Chinese scientists developed quantum computer with 113 detected photons. It can implement large-scale GBS. This Gaussian boson sampling is actually something that if you have a random circuit, how it will provide the output and all those things. So this is a trillion times faster than the world's fastest existing supercomputer and 10 billion times faster than their earlier version. This is the claim they have made. So what they told finally, it would take the fastest supercomputer about 30 trillion years to solve a problem that using 2.0 can solve in just 1 millisecond. This was a newspaper. You can search and check it. Then, okay, such a report is there. Immediately some people will ask, okay, can you see what they are claiming? Is it true? Whether Indian government should be very careful and all those things, whether we can have a research paper. So then what I did, I found out the paper, and we can download physical review letters paper. So this is the paper they published with 54 scientists from 6 institutes, and this is the data. What started naturally long back. Chinese are doing very nice work in this domain. So what they told, looking at that, we understood that they estimated that a sampling task finished by this special computer in about 1.2 hours will take the most powerful supercomputer around 8 years. This is fast for that specific problem. Not a problem that would interest us, but they could obtain a problem and they could show that this is the improvement. So the improvement is not septillion and all those things. So the similar thing is coming up for all the companies that are talking about these things. So this is actually the parallelism slide. Again, things are not coming very well, but this will show that you can have all the patterns in the superposition. And the main algorithms I should tell. One important algorithm that you should learn is Loyal-Souza algorithm, and these are the 4 algorithms that when you start learning, quantum computation can very easily be a 1 semester course, and your professors can offer that also. It's important, very mathematical. You need only linear algebra and basic combinatorics, nothing more than that. There are lots of very good materials, and these are the 4 algorithms which are, first 3 are absolutely can be explained with Boolean functions. We interpret it in that manner, and the 4th algorithm is the famous factorization algorithm. So, and this Grover is a person from IIT Delhi. So there is good Indian connections in quantum for quite some time. So these algorithms can be understood very well, and there are certain cryptographic implementations corresponding to this. Hardware issues, very few countries or companies will be front runner in fabrication of quantum equipment. As in case of classical computational and communication equipment, it is expected to purchase quantum equipment from external agencies only, because we don't think that in India suddenly we can build quantum computers. So the main question is how to evaluate the third-party quantum equipment. Is it really quantum? Was there any kind of trapdoor? So theoretical results will not be of great help. We need to access those computers. Our country must buy those computers, or our students should go to Google or IBM. Many Indians are working in those companies, but we really do not get much information at this point. Software and algorithmic issues, we are very good in that. Nobody can stop us. So theoretical analysis of existing quantum algorithms, we can write paper, we can analyze, exploring new algorithms. There are a long list of algorithms available in this quantum algorithm zoo. Need to understand how fast these algorithms can be implemented in classical environment, maybe using supercomputer, because then only we can think that whether we need a quantum computer or not. We should carefully choose or explore the problems of exploiting quantum algorithms. And quantum algorithm, this machine cannot be quantum, so we will always communicate with quantum computers by classical things, right? There are lots of photons moving around in this room, but we cannot grab them. So similarly, we need to connect our classical machineries with quantum machineries. So lots of classical pre-processing and post-processing are required. In QKD I have not discussed, but there are also lots of classical post-processing are required. So that it is also a huge area where the classical and quantum things should, for that interfacing, we should put a lot of effort. So, and basic idea is we need quantum preparedness. We cannot buy a quantum computer, but we should learn and understand, and we need to implement the post-quantum cryptography on our standard classical machines. So that is the basic idea. In terms of revolution, you can tell that other than French Revolution or November Viplov, there are also some revolutions which are related to technology. That actually turns out to social revolution. So 1760 to 1840, we can call it as industrial revolution, where muscles were replaced by machines, and as we understand, for computers, our brain would be replaced by machines, and there are lots of issues, social issues related to that. Already that has started, starting from 90s or after internet. We are all somehow in the cage. We cannot come out of this. This is everything now we have. Even if we tell a lot of very nice things that we should not use WhatsApp and all those things, always we are with these machines. So we have to understand how it can disrupt our life, and if a quantum computation, if quantum computers come in the market, you won't get it in Chandni quickly, but it will disturb other countries and all those political situations, the social situations very big. So the point is now we are in the middle of the computation related revolution. It will come into history maybe after 100, 200 years. It's not like Shingu Nondigram, or we have in 2006 you have the incident, and 2013, 14 you have in history book. Right. It's not like that, but it will come, sure. So that kind of thing, this will happen, and then we are exactly in the boundary of classical computational revolution and quantum computational revolution. You will, in our life, we have seen the complete revolution of classical computers, 70s, 80s, 90s, how it moved and where we are. So there is a good chance that around 2030, 40, 50, you would be looking at this change when quantum computers come. And the final note is, quantum computer, I do not think that they would add anything in much in artificial intelligence or all those areas very quickly, because the computations are huge. Even if it cannot adapt some kind of cryptographic problems, even small problems, then putting it in market domain with lot of uncertainty and errors is not very clear. So for this time, at least during next 10-20 years, the main risk would be on the security system around the world if a quantum computer comes. So Very simple, better be prepared in the cryptographic domain because that is not an advantage, that is a risk. If a quantum computer comes, we should be prepared with classical post-quantum cryptographic algorithms, and also theoretically in AI, ML and all those areas, we have a lot to put getting our understanding from this quantum computational model. So I have not talked anything technical as Abhishek already told me. I hope I could communicate a little bit to you from where you can start studying this. Thank you. So I think there should not be much questions on this because I have not talked anything technical. So what we do for mathematics students or other students, we can push Abhishek to have at least a 5-day workshop first on quantum cryptography and all these things, and then a 1 semester course in quantum computation under Crow.
Still, any question or comments? Anybody? So very quick questions or comments?
Very quick questions or comments from anybody? If you have. So there I can see few faces. Yeah, please.
Be careful, if I take a class later, then I will ask you questions.
So why have you not moved towards symmetric cryptography or private key cryptography?
Yes, symmetric cryptography is, the effect is not devastating. In symmetric cryptography, so far, the Grover's algorithm is used to attack the system. So what happens when you are factoring, then you only have sub-exponential algorithm in classical domain, but polynomial time algorithm in quantum domain. So the difference is huge. You can immediately bring it to very low computation and attack the system. In symmetric cryptography, the attack is using Grover's algorithm. What Grover's algorithm tells that if earlier your search requires capital N time, then now your search will be root over capital N time. So square root is different, not sub-exponential to polynomial. It is only square root. What does that mean? If there is an n-bit secret key, then 2 to the power small n, say 2 to the power small n many attempts you have to make in classical computer. And root over of 2 to the power n, that is 2 to the power in power n by 2, that amount of computation you have to do in quantum domain. So what you can do? Earlier your key size was say 128. If you can double it, immediately your purpose is served. So in symmetric cryptography, if you just increase your key size to double, you are more or less safe. So that is the reason we have a lot of papers in this we write, and there are many papers also where the symmetric crypto systems are attacked using classical algorithms, but that is not devastating. So earlier you are buying something with say 10,000 rupees, now you are buying with 1 rupee. That is something like sub-exponential to polynomial. But exponential is 10,000 and root of that is 100. That problem is there for symmetric cryptography. So it is less devastating, so we generally do not talk much. But there is a huge difference. Good question. Thank you.
Sir, I have a very basic question.
I also know very basic.
In quantum cryptography, we always consider probability as square of amplitude modulus. So, what is the intuition behind it? Why square of amplitude modulus?
Yes, that was also, I should say. Getting old, so missing important things, but thank you very much. Again, the signs are not coming properly. Every qubit, when you work with the qubit, finally we have measurement. Without measurement, we cannot observe anything. So it's something like a coin is tossed. So the coin is moving, we can do some computation there, but to understand anything, we should allow the coin to drop and expect that it is not a Scholle coin. Scholle coin, many of you do not know about it. Scholle coin, there was a toss, we should watch that movie also. Our childhood movie. So the coin was vertical. So, but generally you will get 1 or 0. So this measurement is very important to finish the algorithm in quantum computation. When the algorithm is finished, there is measurement. What is the measurement? that if the quantum state is alpha 0 plus beta 1, then you measure it in 0 state with probability mod alpha square and measure it in 1 state with probability mod beta square. So whatever algorithm you are writing, you will understand when you read the algorithms that a qubit after the algorithm, when you are observing something classical. This is very important. At that point, when you are observing the output with certain probability. And from that output, you have to interpret. So that is what the measurement part is involved with the probability, and always whatever we do, probability is involved in this. Some partial answer. That.
No, my question is why mod alpha square of getting 0 state?
Oh, this is the model actually. This is when we consider, like when we, I understood, possibly understood what you were telling. Like when we have a battery, then the top side of that we connect, we tell that 1. And the bottom side we connect, we tell that 0. Now, when we are taking an electron or photon and we are considering the spin of that, the simplest model for computation implements that as alpha 0 plus beta 1. Why? Because the very basic idea of uncertainty, what does that tell? That if I have one electron moving in the orbit, if I know very well the momentum of that, I will not be able to know the position of that, and the other way around. Similarly, here also, when I model this, I cannot tell or I cannot control the spin very well. So it would be something like something into 0 plus something into 1, where the physics is modeled in mathematics as alpha and beta, where alpha and beta are complex numbers, and mod alpha square plus mod beta square must be 1 because we are considering in terms of probability. So it is just a normalization. So this is the best physical model of the physics part, which we do not know much. Like battery and all these things, fine, good, we know, we have worked with this earlier. But the quantum computers, how they would be, another very interesting thing that I should tell when you ask this question. In classical computer, we have circuits. So something like electrons are moving. So chips are fixed at one point. Chips are fixed, data is coming from left to and going out to right, say, or coming from right, going out from left, something like that. So data is moving, but the circuit is fixed. In quantum computational models, the data, that means the qubit, is a photon or something, an electron, that is fixed. And some light is coming on that, which is working as the gate. So the light is acting, some light kind of thing is acting, then another light emitting part is acting. So the data is fixed, the circuit is moving. That is another very big difference in hardware implementation. But unfortunately, I have never accessed, I have accessed all the classical computers, opened them, worked on that for last 30 years. But in India, I didn't get any opportunity to open those things. That how an electron or photon should be understood as alpha 0 plus beta 1, that basically I have. I don't have good knowledge of that.
So, okay, so
Yes.
Sir, earlier you said that when somebody tries to break into a qubit and the information gets lost or the qubit gets destroyed, but does it mean that we lost the information inside the qubit?
Yes, completely. So when I have alpha 0 plus beta 1, say you have prepared, say you have a device, you have prepared a qubit where alpha is 1 by root 2, beta is 1 plus I by 2. But I get this qubit from it and I measure it in 0, 1 basis. Once I get 0, it becomes 0, everything is lost. I don't know what you have.
But isn't it a disadvantage of the...
No, this is not a disadvantage. Because first of all, if you know that, that implies that you are breaking some laws of physics. So that is the first thing. Qubit, from that you cannot get any information, that is by the theory of physics itself. And even with that disadvantage, we have other facilities that we can use in the computational model to get something. So what you are telling, if we have a qubit and know everything out of that, then the problem would be that all the quantum cryptographic systems that are based on quantum mechanisms, everything would be broken. So that is the disadvantage. So I understand what you are telling, that we cannot extract the information from a qubit, but we can extract a little more than classical, and that's enough for the improvement, because the improvement is exponential. In classical computer, if you have a speed, say with 32 bits you are working, and next you are working with 64 bits. So you are getting some advantage, but the advantage is not exponential. In quantum case, in one qubit, if you get the advantage which is 2 to the power 1, 2 qubits you get the advantage 2 to the power 2, n qubits you get the advantage 2 to the power n. So even if you do not have knowledge about certain things, using that immediate development of n to 2 to the power n, you might extract some additional, not might, you can extract some additional information. For that we have to study it.
Okay, so that would be the end of this. So I hope that no more further questions. So now I hand over this mic to Ritambo. You have some questions? So very quick question, because Subhamoy এরপরই যাবেন হচ্ছে আমাদের এই ইউনিভার্সিটিতে একটা ডিবেটে, সেখানে তোমাদের সবার কিন্তু আমন্ত্রণ রইল।
এটা কিন্তু আমি জানি না তুমি নিমন্ত্রণ করতে পারো কিনা, আমি অন্তত পারি না।
স্যার বলছি স্যার, নতুন কোয়ান্টাম অ্যালগরিদম নিয়ে এক্সপ্লোর করার জন্য পাথওয়ে বা রোডম্যাপ কি হতে পারে?
একটা কোয়ান্টাম কম্পিউটেশনের বেসিক কোর্স করে ফেলতে হবে, তাই করা আছে, সেটা আগে করে ফেলতে হবে। মানে যেমন ডিজাইন অ্যান্ড অ্যানালিসিস অ্যালগরিদম কি অফার্ড হয় এখানে আমাদের ক্লাসিক্যালে, আমাদের ডিজাইন ম্যাথস ডিপার্টমেন্টে বা কোথাও ডিজাইন অ্যান্ড অ্যানালিসিস অফ অ্যালগরিদম কি অফার্ড হয়? We have to have some basic courses of computation.
Sir, can we implement using classical computers logic?
There can be simulators, and also IBM has some simulators and some actual machines. Now they are asking for money. Initial last 5 years they have given something for free, and naturally this is business. So like the geophones also. Initially they won't ask any money, and later when all the computers are gone, they will ask more money. So IBM is now doing that. So IBM initially has given us some access. Now the only access is in the simulators, not in actual quantum computers. But for our purposes, for research purposes, there are enough opportunities to write those programs and see that.
First of all, thank you, sir, for this insightful lecture on this quantum cryptography. Now, I would like to call on stage Professor Abhishek Adhikari to present our token of gratitude to Professor Subhamoy Maitra. With this, we have reached the end of the seminar. We express our heartfelt gratitude for this astounding number of registrations and support. We at Crow plan on bringing such ventures in forthcoming future, and therefore we would like to all of you to join our WhatsApp channel via the presented QR on screen to stay updated with news of such events and opportunities. This year, we are also going to host our first edition of our annual mathematical fest, Symmetry, on 19th of September 2025. And so we would like to invite you all to join us for the upcoming journey. With that, we would like to conclude our event for the day. Thank you all again for being such a wonderfully supportive audience. We hope we would meet again in the upcoming events. Good day.
So thank you all. So I was just looking at this attendance sheet. It looks like more than 140 participants are present over here. So it's really a great